The lunar rovers we had developed, that was developed by the Marshall Space Flight Center and was deployed from the lunar module on the moon that the crew used. Initially, when they had gotten out on the moon and the vehicle had gotten cold, they started having some funny indications. The battery meter that would indicate the state of charge on the battery would start going in reverse and show the battery as being charged instead of being discharged at some constant rate. The voltmeter would act up and at times be reading and at other times not be reading, and we had a couple other indications. The lunar rover mission proceeded with those anomalies, however, as they didn't interfere basically with the driving. And the crew, the ground flight controllers, learned to try to keep track of the battery amp hours and so forth, even though the meter was acting up. But Marshall Space Flight Center was running an investigation trying to understand these seemingly unrelated anomalies. There were 3 or 4 different instruments and so forth that were relating these anomalies, and it all showed up. And when the lunar rover would warm up, these anomalies went away. It was only when it got real cold that they showed up. It turns out the lunar rover was put together with wireless and so forth, so we didn't have any end-to-end system schematics. So I proceeded to start putting together electrical schematic of everything based on the wireless that they had for the lunar rover. And then, of course, we carefully were looking at all the flight data. And in laying those schematics out, or drawing the drawings out, I happened to notice that, lo and behold, something I was started out looking on the schematic first was the grounding system, because anytime you have a lot of different unrelated electrical anomalies, there's a good chance the electrical system, the grounding system associated with the electrical system, is involved with a problem, and you don't have good grounding somewhere. So I started looking at the grounding return system, and then lo and behold, these various instruments that were having problems, all of their returns were coming back to a common spot. It turns out there was one splice that was used to the big negative on the battery, and because the battery applied the power, it was a heavy gauge, very large heavy gauge wire, and the splice was large. But then you had all these small instrumentation wires from the electrical unit that was monitoring the battery charge to the voltmeter and amp meter and some of the other items were going into the same splice. Well, it turns out that anytime you have a large cable in with a bunch of small cables, and then you try to have a clamp that you crimp around that, the large one tends to protect, and the other larger wires that were in there tended to be properly clamped, but the small wires that were in that same clamp tended to not be clamped so well and were actually loose. And sure enough, when you looked at the electronics on the amp hour meter, it used a column of mercury that you flowed current through to transfer the mercury that then gave you a readout on the amp hours remaining in the batteries. Well, it turns out that when you lost the ground of that electronics box, you had a sneak circuit, or you had circuitry in there trying to seek another ground. And it turns out to be able to pick up a ground from one of the cases, turns out the leakage current from one of the transistors, which was about 10 milliamps, would end up flowing back in the reverse direction through that column of mercury, trying to get to a proper ground, since the ground that through the main ground had been lost. And lo and behold, that when you took that 10 milliamp current and run it in that amp meter, it would give you the exact reading. It gave the exact increase in amp hours on the batteries, which was the exact reading that the crew was reading on the ground. So that pretty much proved that that was the cause of that unexplained amp hour meter. It turns out that the approach Marshall engineers had used in their investigation was they had called in, it was these various vendors from their black boxes, and had them do a presentation on the failure modes and effects of their particular box. And the vendor for the battery charger came in and was unable to show any failure modes that would reproduce the condition he had in flight. In each one of those cases, of course, that particular vendor assumed that everything outside his box was proper, and he was therefore only analyzing the conditions inside his box. And therefore, as they brought in each one of these groups, that's the reason they never were able to pick up on the fact that it's the external wiring in the Lunar Rover, and it was this loss of ground that was causing the problem. We then went in to check, because the Lunar Rover itself had been put in a thermal vacuum chamber and gone to high temperatures and low temperatures and got qualified that way, where we got to checking, well, why didn't this problem show up in the thermal vacuum chamber when they went to low temperature? Well, guess what? The qualification configuration of that Lunar Rover was different than the flight. It just so happens that they used solder joints for all the connections on the qualification unit, and they used splice connections on the flight unit. So one lesson here, of course, is you had a configuration difference between the qualification unit and the flight unit that got to you. At the same time, when we looked at the size of the gauge of wires and the number of wires in that crimp splice, it violated the crimping criteria we had on the spacecraft, the Rockwell spacecraft for command and service module, which specified a maximum of only about 3 wires, and you could only vary a couple of differences in wire gauge on that splice. You had to go to other splices if you had to do multiples, and you had different wire gauges. So it violated the design criteria that Rockwell had in place for their electrical design in terms of splices.